Chemistry, Module 6, extra practice problems. This is number 6 through 10. We've already done 1 through 5. If you have questions on those, you've got to go back to another video. But we're going to deal with the extra practice problems, which are in the very back of the book. In this text, it is on page 574. So have your answers, have your calculator, work along with me. Here we go. Here's the question for number 6. We've got magnesium plus water gives us a magnesium oxide and H2 gas. It is already balanced for you. A few things just to mention in the parentheses. This is a little S. That means this is in its solid form. Water in its liquid form. Magnesium oxide, hydroxide, this is in a solid form. And our H2, which is a homonuclear diatom. That's why it's paired up with itself. It can't be H alone. That's in gas form. Okay. So we're going to start, and they ask how many grams or what mass of magnesium do we need to make 5.6 times 10 to the 4th grams of the magnesium hydroxide on our product side. So they're saying, hey, we made this much. How much do we need to make it again? First thing, we can't communicate in a reaction using grams. We have to use the language of moles. So let's turn this thing into moles. First one, we're going to turn this into a mole. And how we do that is we start with what our grams are on top. Times 10 to the 4th, that's is grams. And we need to multiply it by the grams to mole ratio. And each of these ratios are unique to the specific compound or element or atom we're using. So in order to find magnesium hydroxide, we need to go to our periodic table. And the first thing I need is magnesium. Their atomic mass unit is 24.3. I'm just going to write that little up here because I'm going to add these all together. Oxygen, I know because we do that one a lot, and it's 16. And oxygen, we're going to give it a 1. Now, because our oxygen and hydrogen, our 16 plus 1, that'd be 17, is in parentheses times a 2, we have to double both of those numbers. So 17 times 2, that's a 34. And add that to our 24.3, 58.3. If you didn't do it that fast, you're totally fine. I'm just going to double check that I did my math even right because I do it kind of fast in my head. And I do make mistakes. Trying to remember what question we're on. Okay, 58.3. Yay, I did. So what this number means is 58.3 grams is equal to 1 mole of that substance. So we can put them into a ratio form. Now it can be grams on top and moles on bottom, or moles on top, grams on bottom. It doesn't matter because they equal 1, but what it does matter is that it goes with our equation. Now this has grams on top and we want it to end up with moles on top. So we need to multiply and put our grams on the bottom because grams divided by grams is 1 and they can cancel out. And this is 1 mole. You can stop and write that number in and that's totally fine. That shows your progress. But I'm just going to keep it going as one equation. The next step in our process is using stoichiometry, and that's using the stoichiometric coefficients of the numbers. And if there is no number, it's a 1. So this is really easy. That says for every 1 mole of magnesium, we make 1 mole of magnesium hydroxide, 1 to 1. So that's a pretty easy one. The next thing we do, so what actually this did is this put us from moles of this one. Now we're into moles of magnesium. That's what our number is as we move across. So this is now, we canceled out MgOH. And now we have Mg up here. So these canceled out. So we're rolling with magnesium on top. And now we need to find the mole to gram ratio of magnesium. We have moles on top, so we need to put moles on the bottom and grams on top. We already know this one because we found it before. It's 24.3, but we don't add it to anything because magnesium is all by itself. So then all we're going to do is multiply this straight across. 5.6 times 10 to the 4th divided by 58.3 times 1 times 24.3. And we get, they always put this in such simple 23,000 grams. Now, if you are going to be putting that in scientific notation, which you don't have to do, although we do get, we only get two numbers. That's why we got 23,000. So if you typed that all in, I'll do it right now so we get our raw number of what we're dealing with. Let's see, 5.6 divided by 58.3 times 24.3. It'd be 23,341, and then this infinite number of decimals. But we only get two significant figures. So we start at the first two and a 3, and then we look at that third one. Do we round or do we drop it? And since 3 is less than 5, we drop it, and we end up with 23,000, or 2.3 times 10 to the 4th grams. And that's the answer to number 6. Number 7 is asking for which of these equations is in its empirical formula. Now, empirical formula just means the base ratio of atoms to each other, of elements to each other. And so if you cannot divide all of those things by a similar number, or there's no common factors, they are indeed in empirical formula because you can't reduce them any. We take them from empirical formula and then we multiply by their factors to get them into their actual formula. So let's look at A. S would have a subscript of a 1 and O is 3. They have no common factors. So this is an empirical form. K2, S2, O3. There's nothing smaller than a 2 and a 3 that can go into the same number. So this too is an empirical formula. C6, H12, O6. These can all be divided by 6, which would mean the empirical formula would look like CH2O. That would be its empirical. So this one is not in its empirical form. We've got P2H4. These can both be divided by 2, which would tell us that its empirical formula is actually pH2, which says no, this one is not its empirical formula. Number 8, I'm going to read it out. Decomposition of a 100 grams of a dark green powder, and it yields 39.7 grams of potassium, 27.9 grams of Mn. Shoot. I don't know that one off the top of my head. If you guys know it, good job. You totally beat me. And then an unknown amount of oxygen. What's its empirical formula? So all I've done so far is wrote down our masses. We could easily figure out our X, right? We can just do some math about that one. And so we're going to write it. These are our unknowns, X, Y, and Z. And then we're going to write our decomposition formula. When we decompose, we take them into their individual elements, and then we have an O. I hope you already are like, Serena, red flag, because O's never travel alone. They're a homonuclear diatom. We have to pair them up. I'm going to put a 2 on it. Okay. The next thing we're going to do is figure out our grams of oxygen. Now, matter cannot be created nor destroyed. It just changed form. So if we start with 100 on this side, we end with 100 on the other side. So we can simply take our 100 and subtract what we already have, our 39.7. And then also subtract our 27.9. And that tells me that I have 32.4 grams of oxygen gas. I'm going to write that in right here. 32.4 grams. Okay. Next step. The next thing we're going to do is we're going to put these into moles. It would be so nice if we could just use these gram ratios, but that is not how anything relates to each other in chemistry. It only relates in moles. It's like our special conversion factor that everything gets plugged into. So let's get potassium into moles. We've got 39.7 grams of it. And to convert it into moles, we're going to need our periodic table. Potassium is 39.1. I'm going to write that one on the bottom. 39.1 grams is 1 mole. So let's see how many moles of that one we have. 39.7. It's going to be pretty much close to 1, right? Divided by 39.1. 1.015. So we're going to call that. We were given 4 significant figures, and then we were given 3. So we really only going to keep 3. We're going to call it 102. That's its number of moles for potassium. Okay, let's figure out the moles for the other 2. Okay. I had to look up what Mn was. It's manganese. I don't use it very often, so there you go. If you knew that one, kudos to you. Let's find the moles of manganese. We start with 27.9 grams of it. It's atomic number 25, but its atomic mass is 54.9. We put that on the bottom, 54.9. 1 on top. You should be able to look at this briefly, be like, that's going to be about 2. Oops. Okay. I said 2. I meant that there's 2 of these in here, which gives us a 0.5. That's why it's nice just to put it in your calculator. So we have 0.508 moles of manganese, and we just have oxygen left to do, and then we're good to go. Okay. We figured out that you end up with 32.4 grams of oxygen. That's what's right here. The atomic mass of oxygen, because it comes in a pair, is 32.0. And this is 1 mole on top, and this is grams on the bottom. 32.4 divided by 32, it's going to be 1.01, and that's moles of O2. So I've been writing up here at the top how many moles of each one we end up with, and now we're going to put them into relationship. We're going to add them all together. So we have our 1.02, our 0.508, and our 1.01. We add those all together to give us our total number of moles. Hold on. Oh, that is how it's broke down. So if we break it down with that, then it tells us how many we start with, and we can get a ratio of them in their totalness. Let's see, hold on. Sorry, I was looking at what the book says to do and then what I do, and they are just a little different. So I'm just going to walk through the steps. So if we were to plug these in, this would be a 1.02. Like if we were going to balance this equation, a 0.508 and then a 1.01. But we can only use whole numbers. We can only do like 1s, 2, 3, 4. We can't have this 0.5. And so to change all of them into whole numbers, we divide by the smallest number. So if we divide all of them by this 0.508, we end up with 2 potassiums, 1 manganese, and 2 O2s. Now that's what it gets broken down into. So you can put that forward and you plug it into these numbers. So we have K2, Mn, O, and then we have a 2, and then it's a 2. So we end up with a 4. And this is our empirical formula. Because this is a 1, 2, 4, we can't break them down any smaller. This is its empirical formula of pen. Did they even tell us what it is? No, so it doesn't matter. We won't worry about it. Number 9 says the mass of the molecule above, that's this one, is 197.1 AMUs. What's its molecular formula? So we need to break down what this actually weighs and then how close we are to that number, or by what factor we need to multiply it by to change it. So we have O is our 16.0, our potassium. Oh, we just had these all written down, didn't we? Hopefully you still have yours. Potassium is 39.1 and manganese is 54.9. So let's multiply those numbers and see how close we are to 197. 39.1 times 2 plus 54.9. There's just a 1 here. Add that to 16 times 4. You get 197.1. So because the molecular mass is the same as the empirical formula, This is both the empirical formula and the molecular formula. They're the same, which happens with a number of molecules, just not all of them. Okay, last one. This is the empirical formula. This is its most basic, simple form of their relationship with each other. They want to know what the molecular formula is if it weighs 60 AMUs. So the first thing we need to do is add up what our current empirical formula weighs. So carbons weigh 12.0. Hydrogen times 2 weighs 2. Oxygen is 16. So we have 30. This is 30 AMUs. In order to get from 30 to 60, I have to multiply this by 2. If it's easier for you to divide it because you can't see the answer, that's totally fine. But what do I have to do to 30 to get it to 60? Just times it by 2. So I need to multiply this entire thing times 2. But we don't leave it in front. We're going to put this as its subtext. So now we do a C2. 2 times 2 is 4. And then our oxygen is 2. There is your molecular formula for this empirical formula. So this sums up Module 6, specifically in the extra practice problems in our Apologia text. I hope this was helpful. Okay, best of luck.